then we're talking about the quantum critical point between the transition from a semi-metal to an insulator with Néel order on the honeycomb lattice of the Hubbard model. And then there's graphene itself, which has long-range Coulomb interactions, okay? And for these models, we'd love to be able to compute the conductivity. So we are talking about frequencies much smaller than the bandwidth, which is no problem, because that's electron volts, but of order temperature. Be bigger than temperature, smaller than temperature. So the simpler case is to consider the bigger than temperature. So for free Dirac fermions, you can just do, it's just a one loop calculation. It's just all spelled out here. You just have to do those integrals, and you get 1/4 in units of E squared over H bar, which is pi over 2 in units of E squared over H. Okay. Then I jump to this. What about what happens here? Well, if you take graphene with Coulomb interactions, we know actual graphene is a semi-metal. So interactions can't be that important because it's not an insulator. It's semi-metal. And if you look at the effect of interactions, you find that they're characterized by a fine structure constant. There's also a dielectric constant here, which is of order 1 in real graphene. By putting substrates, you can make it even smaller, and so on, by making a dielectric constant large. And then what you find when you do analysis of higher loop effects, this is sort of the screening effects here. So what's happening in graphene, you would think that because of absence of any density of states of Fermi level, there's no screening. So that would mean that interaction should be stronger. But on the other hand, you have less density of states, so scattering will be weaker. So anyway, so you can formally address this by doing an RG calculation. And what you find is that when you go to higher orders, that this alpha becomes a running coupling constant, much like coupling constant in quantum chromodynamics for the strong interactions. So in the strong interactions, we have what's called asymptotic freedom, that you go to very high energies, you see the quarks. Here, it's the opposite. When you go to very low energies, you get free particles. So alpha goes to 0 at very low energy. So there's a negative sign here. In QCD, you would have the opposite sign. So this means that depending on the scale you're looking at, which is this case is the frequency itself, alpha will go slowly to 0. So this tells you that alpha is the effective coupling constant of the theory is logarithmically small. Okay, so now you can just do perturbation theory in alpha, or E. And I think it's still quite a mess. I think these things have been computed. You get terms of order alpha, so there's a correction, which is logarithmic in frequency, okay, which it's not quite Planckian, and so on. All right, then what about here? So this is something I haven't quite discussed. So here what you will find, you get to leading order, you'll get pi over 2, but now you find you have these coupling constants lambda and u, not alpha. This is alpha went to 0 for this problem. Here, at the critical point, they go to some fixed point values. So you have to do a calculation. So it'll be of order lambda star, what did I call the fixed point? Lambda c, uc. So these are some numbers that you can determine from RG, and you'll just get a pure number, and it's universal. In other words, it doesn't depend on anything other than the symmetry of the theory. There's some numbers here, so you'll get a conductivity which is corrected from pi over 2. So these numbers, not for this model, but in recent years, have been very beautifully determined by bootstrap methods. They know the analog of this number for the Wilson-Fisher O2 model to like 4 decimal places now using bootstrap. I suspect they could even do Grosnovo-Yukawa, though I don't know if they've done it. But this is a solved problem using the bootstrap methods. Certainly not something I can talk about here. Because and the reason this is the simplest case is because it's actually a conformal field theory. Yeah.
Super tiny details. The log omega corrections they come from better RG than the alpha square, or they come exactly from the RG with the minus alpha square beta function?
Well, I mean, there's a running coupling constant, and then there's also the expression for the conductivity.
Of course.
Which depends on alpha.
But if you plug that RG solution with the alpha square into the conductivity, you will get this log
the
omega.
leading term, right.
Cool.
They're also, yeah, I think that's all you have to do. But you can also do some integration of coupling constants of RG. And it's all kinds of logs, and it's not very elegant. This is very elegant. You just do perturbation theory.
Just trying to follow the logic. And the correction lambda, depending on lambda CUC, is this order 1? Is this subleading? How is that?
So it depends on how you do the calculation. So if you do the epsilon expansion, these are small, and they're of order epsilon. And epsilon means 4 minus d, where d is the space-time dimension. If you do the 1 over n expansion, then this will be small by 1 over n.
It is 3 minus d, right? You are in 2 plus 1.
Sure, to space-time, d is the space-time dimension, so 4 minus d when d is space-time.
Okay,
yeah.
cool.
Yeah, 3 spatial dimension is what you have to expand about. But people generally do the large n expansion, where n is the number of Dirac fermion flavors, which is quite large anyway, yeah.
So regarding this bootstrap that you said, so they feed the, I'm guessing that they are feeding the symmetries, right? And then the unitarity, and then at some point, is this model is actually sitting somewhere of those, I mean,
so this is
possible.
This is a very special point I'm talking about.
Yeah.
The critical point.
No, I'm talking about how they find the lambda C and UC using the bootstrap.
Oh, bootstrap doesn't do it that way.
They
They just get the conductivity. They just give you a number.
They just give you a number.
Bootstrap doesn't know about lambda or U or anything.
Yeah, but it does know about, because you need to feed something, right? I'm guessing
Yeah.
that they are feeding the symmetries.
Yeah, that's all you need to know.
Yeah.
That's all you need to know.
Okay.
Bootstrap, you just tell them I have one scalar operator with this symmetry, and I have one fermion operator with this symmetry. Find me a fixed point and tell me the conductivity. And they go to the big computer and they tell you a number.
Okay.
It's amazing, but that's all you need to know. They don't know. They don't tell you it's 5-fold field theory or anything. Those are just very primitive tools we use when we want to do some epsilon expansion or something, compared to Bootstrap. But yeah, when that's both the plus and the minus of Bootstrap. With Bootstrap, you don't need to put in very much, but then you don't know what you're getting also. You have to match it with other results to see some idea of what you... Anyway, I don't want to go into a debate of Bootstrap here. Yeah, okay. Yeah, okay. This is not a course on Bootstrap, so I will stop that discussion. All right, so now I want to fill this part, of which we know much less. What about frequency smaller than temperature? All right, one thing at least we can do is we can do here. We can do this, free fermions. All I have to do is to go to these graphs, and simply convert this D3P. All I have to do is to take D3P, which is and replace it by D2K over 2 pi squared. Here is 2 pi cubed times T sum over Matsubara frequencies. Basically, I just take the same expressions and just convert this integration over frequency to sum over frequency. That's all. This is simple enough, you can actually do it. And it's very important you get the exact answer. Then you have to analytically continue, okay? So this is the imaginary frequency. This is the frequency planes. And you're getting some results at the Matsubara frequencies, which are 2 pi nt. And then from there, you have to go to finite frequency, physical frequencies, which is the real axis. So I did that. You evaluate those integrals, you do the analytic continuation, and what you get, okay, maybe I'm jumping ahead. I'll come through. You get this answer, okay. Very strange looking answer with a delta function at 0 frequency. Okay, so if I plot this answer, this is what it looks like. So at high frequency, it's pi over 2, that's up here. And then it seems to go to 0 with a delta function at 0 frequency. Okay. So yeah, maybe I should also show a little bit about this phase diagram. So this is what we're doing here. Yeah, so this would be for the middle line here. So the middle line, you have the phase transition from nail order to semi-metal. And this is temperature. And we are studying what happens at this point in this region here, along a line here. But it turns out that the result actually applies in a whole fan, because in this region, temperature is more important than the deviation from the critical point. Okay, so it's not as if you have to fine tune right here. You can be sitting anywhere in this fan, and you will see the physics that we are discussing. Okay, so coming back then to free Dirac fermion, this is what you see. So over here, we know the answer, because it's a free theory. It's the only place we really know the answer. It's E squared over H, and there's various constants which I have not written down. Some number times temperature times delta of omega plus 1/4 tanh omega over T. Actually, this is true for all frequency. Tanh omega E squared over H bar then. Tanh omega over 4T. Okay, so now when omega becomes very large, this tanh becomes 1, and it's just exactly this answer. But when omega is small, this constant comes back down to 0. Oh, I'm going the wrong direction, sorry. Yeah, comes back down to 0, and you have a, okay. So first thing to notice is this, it's a strange looking function, but it has all the right scaling properties. It's still of the form, which is what I showed before. The first sigma of omega we find is exactly E squared over H times some function of omega over T. Some strange looking function, but it is a function of just of omega over T. Is just a function that's singular. This is also delta of T times delta of omega. Keep in mind, T times delta of omega is just delta of omega over T. So it is a scaling function, but it's a singular scaling function. Fine, okay. So scaling works, it's just things are very singular. So how do we think of this? So what's happening here is the following. You have this Dirac node, and you're at finite temperature, okay? So you're at finite temperature, you're thermally exciting particles here. There's a negatively charged particles here and a gas of positively charged particles here. And then you apply an electric field, and they're going to now move in opposite directions because they have, when you apply a field, so there's negatively charged particles here and positively charged particles here. When you apply a current, the current will, apply a voltage, sorry, the current will flow in the same direction, but the momentum will be in opposite directions because they have opposite charge, okay? So now what happens is that, so that's for free, so it's these excitations with particles and holes with currents flowing in the same direction and opposite momenta that gives you this delta function. So they just keep flowing forever. They're free. You thermally excite them and then they just flow forever. That gives you the delta function. So there's some finite thermally excited density of particles. All right. But then what is going to happen then here? Well, now the point is now here, there are interactions, or even here, there are interactions, but these interactions are in this case universal, just lambda c and uc are going to affect collisions of these particles. And this alpha also, now we'll take the point of view at these small frequency smaller than temperature, alpha is about a 1 over log temperature, so it's about a 1. We just think of alpha as some slowly moving constant of about a 1. So it's almost like the same thing as this case. So these particles that are moving in opposite directions, particles and all, will collide with each other. And since they have net zero momentum, there's no, they're going to collide and move the other way. So because of all these collisions, the current will relax to 0 because the momentum is 0 and the current is 0. That's the final thermal equilibrium state. Okay? The net momentum of the current carrying state is 0. That's very, very important for graphene and for this relativistic system. It has current carrying states which have 0 net momentum, which means that they can relax to 0 by collisions. Because current is not conserved, momentum is conserved. Charge is conserved, momentum is conserved. Current is just the current of the dense conserved charge. It's not itself conserved. Okay, important thing to keep in mind. All right, so you're going to get lots of collisions, universal collisions. So what you expect from these collisions is that this delta function, just think of it in Drude theory of gas of particles and holes. This delta function will then broaden to a Drude peak. So it'll be a smooth function. Yeah.
I have a quick question. So you mentioned this result with the hyperbolic tangent and the delta. Is that for free Dirac fermions?
Yeah, it's free.
So then where are the collisions coming from here?
Yeah, so this is the complete, and now I'm talking about this case. I'm not talking about, I'm done. For this case, there's no collisions, and that is the full answer. That is the answer, it's singular. If you had just had free Dirac fermions, which you never do, that would be the answer you would measure. Okay. This is the complete answer for free fermion. That's it. No more to say. First I'm doing 2 steps. I want to understand physically what is that delta function due to. It's due to this. It's due to thermally excited particles moving in opposite directions. Positive charge in one direction, negative charge in the other direction. Both carrying the same current, but opposite momenta. Okay. And now let's go to these cases. Now, this particle here and this hole here are going to collide. Now they're going to collide because they have interactions. They're going to start colliding, and there's some complicated theory for the collisions. I don't know. So what if the collisions are weak? You can put it in a Boltzmann equation. So this is what we did for a slightly different model in '97 with Kedar Damle. We wrote down the Boltzmann equation for those particles and holes and solved it. And you could only do it when this U star, or this UC or lambda C was small. So it's some collision-dominated regime that you can work out by solving a Boltzmann equation, which only applies because if the coupling is small, which isn't. In the real world, it's not small because we're in 2 + 1 dimension. It only becomes small near 3 + 1 dimensions, but that's all we had. But anyway, from that calculation, we concluded that you're still get a universal function, which is smooth, which looked like to have this shape. Okay, I think that's all I want to say about this topic. There's been a lot of work in trying to improve the shape for this model and other models, using holography, using bootstrap a little bit, using even numerical studies, and it's still an ongoing game. There is ultimately, maybe quantum computers are finally going to solve this problem. I would be very happy. It'd be enough reason for me for there to be quantum computers if they can get this function. Because nobody else can do it. So this is my challenge too. It won't make Google any money, but I'll be very happy. Yes. Yeah, let me just say that here. And this function f will look something like this. That's what we know. Okay, what were you saying? Yeah. That only works in 1+1 dimension. The mapping from R3 to R2 cross S1 is not conformal. If it was, then be no problem. In 1+1 it works, it does not work in 2+1. That's why you need holography, you need black hole. You need a black hole horizon to relax these particle and hole currents. That's where the Planckian dissipation is coming from, the universal collisions of these particle and hole currents, at least in the perturbative picture. Okay, so I think that's all I want to say. Let's go on to topic 2 then. Yes? Huh? Yeah, okay, so here is the same, up to logs. There will be log corrections that don't scale because of the slow flow of alpha, but the experiment seems to work, so maybe the logs are not so important. I mean, it looks pretty good. It was a surprise that this experiment worked so nicely. We weren't expecting to work so nicely.
So wait, the slow flow of alpha is true also at small frequencies and high temperature? I thought it was a result.
Well, it's cut off by temperature. So alpha is flowing. So here what happens, lambda very quickly and just stays here forever. Here, as you lower the temperature, it flows, and it's very, very slowly flowing. So as a dumb theorist, I say, well, let's just keep it constant. Don't worry about its flow. And then in this theory look very similar.
Now, my question was just that I thought this slow flow of alpha was true only for omega bigger than t, not for omega smaller than t. We derived that.
Well, I mean, this is the zero temperature, zero frequency RG flow, and then frequency and temperature provide the scale. So over here, alpha would be 1 over log frequency. Over here, alpha would be 1 over log temperature.
Okay.
Those are just scales that are cutting off the flow.
Okay, good. Was a question? Yes.
It's quite not fundamental, but just out of curiosity, that function that we don't know the exact shape, but we know the general form.
Yeah.
As W grows,
As that what,
omega,
sorry?
as omega grows,
Yeah.
it's going to asymptotically approach something, or was that, or it's going to like? Do we have?
No. So yeah. So this function, as omega grows, must be this value. So that we know for sure. In fact, we know this value. So the only thing about this function we know very well is its value as omega over t goes to infinity. For a certain model that's known very accurately, of course, a free fermion is pi over 2, which was seen in the experiment. So that's the thing that's the reliable result. That as omega much bigger, I should really say this is not really omega. Now that I'm writing it, it's arbitrary general omega. This is for omega. Omega. This will limit to that. Yeah.
Thanks.
Hi. About actually, you said at the beginning of the class that the graphene, the third case, there's no critical point.
It's almost critical if you think of
critical.
alpha as not flowing very strongly.
So the reason it's not critical is because you have these log corrections, and they come from like non-critical behavior.
Yeah. So the statement is what I just said. Alpha is flowing because this 2 is crucial because there's a 2 here. The flow is very small when alpha becomes small. Okay. So it's only logarithmically flowing. So if you don't worry about logs, it's as if it's a quantum critical system. So, and then I would say, okay, but we didn't know how, that was just an argument. It was in our paper. Which paper? This is our paper, yeah. If you look at this paper, this is what we said. And, people were saying we're talking nonsense. So we said, we can just think of it like a CFT and it should have this kind of conductivity. These days when we wrote this paper in 2008, people were doing Landau transport that people had done for semiconductors and applied to graphene. It simply doesn't work. This is the correct. So anyway, this is what we said, and nobody believed us. But now we have this experiment and this experiment, so maybe we were on the right track. So now you see, look at this. This is pretty nice scaling. So maybe that's not such a bad picture.
More questions? So Subir, before you go to SYK, maybe
Yes.
if I try to summarize and perhaps
Please.
trivialize this first part. You're just telling us that Planckian dissipation per itself, even before SYK, is nothing spectacular. You find it in many cases. You have found it in papers 20, 30 years ago. So people make a big fuss about Planckian dissipation these days, right? But all this is story quite
Well, I
old.
mean, I think, depending on how you think about it,
I'm trivializing a bit, but I'm
no,
pushing
I mean,
it.
if you have a scale invariant RG fixed point in the relativistic theory, then at some level it's trivial. Yes, there has to be omega over t scaling. That's what you would say. Okay, but yeah, so however, when you have a Fermi surface, when you have a metal, there's no hope of a scale invariant of a relativistic fixed
No,
point.
that I appreciate.
Okay.
It's all the mapping and calculation and
that's what
approximation we
comes in.
did, and the experiment
That's where
sees it is
SYK
non-trivial. Yes,
comes in.
it's highly non-trivial, that part.
But
Yes.
I will also say in my defense that if you look at the papers before the Sachdev paper, we wrote in 98 or whenever,
98, yes.
some of these ideas were around. And there were people even computing conductivity. There was a famous paper by Fisher, Gervin, and who was the third person? And Grinstein on universal conductivity at superfluid insulated transition. They got it wrong. I mean, they were saying, oh, it's a scale invariant fixed point, and we just put everything to 0, and we just compute sigma. But what they computed was not the DC conductivity. They didn't realize Planckian dissipation at all. They didn't mention it anywhere. They didn't have any omega over t scaling, even though maybe they knew about it. And they took this answer to be the DC conductivity. That was just wrong. And there were all these papers on fractional quantum Hall critical points, which are also relativistic. And people were discussing the wrong answer for applying to experiments. Okay, this is before you were born or something, but I was very much in the field. So it took a while before I think, yeah, so I think this paper did make a significant step that nobody else had realized at that time.
So the non-trivial part is this gross Neveu-Yukawa model. Once you get there,
oh, yeah. I mean,
that is the non-trivial part, that you can map the Hubbard on a comb into that model. But once you get that model, then what we just said will
modulo what I just said about the early days, yes. It is, in the end, if you think about it correctly, it is not that, it's fairly obvious. But everything looks obvious in retrospect.
No.
Okay, yeah. All right, so, but that's a question and segues to the next part. So this is all great for relativistic field theories. And it's nice that graphene is almost a relativistic field theory, modulo these logarithmic flow, okay? So that's great. But almost nothing else is. Any metal you pick up which shows strange metal behavior, it has nothing to do with Dirac fermions. It's got a Fermi surface. So before we go to the Fermi surface case, which I think I will only get to tomorrow, let's think about this in a slightly different way. Another thing about this fixed point of this graphene structure, that its density of states vanishes at the energy, at the Fermi energy, at the fixed point we're studying. And this means it's incompressible. The compressibility is 0 because there's no density of states at 0 temperature. You can't add any particle, remove a particle. The density of states is 0. But of course, once you go a little bit above it, vanishes linearly. And so the whole structure here, relativistic structure, is very much tied to the fact you're exactly at half filling. It only happens at one filling, which is half filling. It's very much tied to that. We very much like to see some other models where you're free to vary the density. You can have any density you want, and you're compressible, but yet it's quantum critical. Okay, so that's the claim to fame of the SYK model. It's the first model like that. And it's even a solvable model. It has no quasi-particles, it has Planckian behavior, and it's compressible. And it can have any density you want. Now, it doesn't have a Fermi surface because, for various reasons, it's got impurities and so on. But those are things we will fix next time. That's the next part that we've been working on, made progress in the last few years. Okay, so now right now we're going to, the aim is to look for some compressible Planckian dissipating system. I don't care about how artificial it is. So let me explain it by just talking about an even simpler system, which is compressible but is not Planckian, which is just free fermions. And now, instead of putting the fermions on a honeycomb lattice with a beautiful relativistic dispersion, I just put them random hopping, okay? You have n sites, and you can hop from any site to any other site. So that's it. Free fermions on a random matrix. So this is a, random matrix theory played a huge role in nuclear physics in the, 50s and 60s. And a lot is understood about it. But here, we're going to apply it in a different way, because we're going to think of a finite density of fermions in a random matrix. So you have a bunch of sites. They can be anywhere, n sites. And you can hop from any site to any site with some hopping matrix element Tij. And you can go anywhere, okay? Here, there, everything is allowed. So you have order n squared Tij, so our n into n minus 1 over 2 Tij. And all we're going to need is that the Tij are uncorrelated random variables. So Tij, TKL, average, and I'm going to make them complex just for simplicity, is equal to 0 unless Ij equals KL. Otherwise, they're uncorrelated. So that's really all. You just have n squared uncorrelated random variables. They form a okay, so now the first thing you want to do is take a random matrix. So basically, you have a complex Hermitian matrix where these are all random numbers. Of course, they're Hermitian, that's all. Just take and find its eigenvectors and eigenvalues. So this has been done. This is the problem that's been thoroughly understood. There are books written on it. I will just talk. So you get some eigenvalues E alpha for whatever set of Tij, you get some eigenvalues. And what all we're going to use right now and compute is rho of omega, which is average of delta of omega minus E alpha average. Okay, so you can do this on your computer in a few lines. I think even ChatGPT can write the program for you. Take a random matrix, 100 by 100, find the eigenvalues, compute the density of states, and then average about 50 samples. What do you get? Okay, maybe ChatGPT could do this while I'm writing it on the board. You get the famous semicircular distribution. Okay, that's the answer. Absolutely, thank you. Yes, of course. All right, so now actually I'm going to do the calculation for you. It's really very simple. Okay, I'm going to do it on the board. So we're going to do it thinking about it as many-body theorists. We know Green's function. So we're just going to do Green's function on this Hamiltonian. So we're going to, our Hamiltonian would be mu. This is our Hamiltonian, period. This, and then this we'll treat as an interaction. We do perturbation theory in Tij. Okay, so what happens then? So let's do that on the board. I think I can erase this. Okay, one very important point for this all to be defined, which I haven't mentioned, is this factor of 1 over square root of n here. Okay. Okay, so first we have just this G0. This is G0, which is 1 over omega, I omega plus mu, just the mu term. Then at first order, we're going to get something like this. You have a site here. You're going to go to some, you're going to have interaction. This will be I, that'll be J, that'll be J, and I'll get Tij. That'll be the first contribution. Now, for convenience, I'm going to take Tij have zero mean. If it has non-zero mean, you just absorb it in mu. So no trouble. That's 0. So now if I average this gives me 0. Okay, so the next order, I'm going to get this, 2 of them. So this will be I, J, K, K. Okay, so I have Tij, Tjk. So now I'm going to average them. Okay, now the only way they're going to be get a non-zero value is if K equals I. Only then is this thing correct. So there's an arrow here. So the way I represent that is putting a hat line here. Putting a hat means this is equal to that when I do the average. And so this becomes I. And I have a sum over J. And there's a factor of 1 over root n from here. And a factor of 1 over root n from here. So that's this 1 over root n. And then the average over t will give me a factor of t squared. Yeah, t squared, which is the mean square value of Tij. Okay, so that, whoops. So that gives, I can write that as a self-energy. So this graph here is the self-energy. And it's very simple. The self-energy sigma is t squared g. Because this is g here, t squared. There's a sum over n, so you get 1 over root n. You get 1 over root n from here and here, and the sum over j, and this is just 1. Okay. So that's the answer at second order. All right, now you go to higher order, and you find that there's no, everything else is down by factors of 1 over n. That is the complete answer. That's the exact answer as n goes to infinity for the self-energy. And you can go to, let's see, third order has to be 0 by symmetry. So fourth order is where the interesting things happen. So, you can get this graph. But this is not a new graph. This is just part of the self-energy. So you can't include that. So the only new graph at fourth order is something like this. Okay, so this is t squared. This is t squared. And so now if you just look at it, there's a 1 over, there's 4 vertices. So there's a 1 over n squared coming from 1 over root n, 1 over root n, 1 over root n, 1 over root n. And then you just look at it. So this is I, and if this is j, well, these two have to be equal. So this has to be j, that has to be I. And then if you look at these two, so this is j, well, then this also, if this is k, then this can't be k because this, which way is this going? Anyway, this has to be basically I, and that has to be I or something. Otherwise, it's all 0. Okay, so basically, at the most, you get one summation of j. And this will be 1 over n. Okay, so you can play around. There's no other graph that survives. N goes to infinity. So this is the complete answer. this is the answer. So now you have Dyson's equation for G, and you have self-energy for sigma. There are two unknowns for each frequency, G and sigma. It's a quadratic equation. You can just solve it. And when you solve it and take the imaginary part of G, you get the semicircle, okay? This is a fun exercise for the tutorial. It's just solve a quadratic equation, take the imaginary part, and you get the famous, this is called the Wigner semicircle law. And it gets you, by this method, Wigner used a far more complicated method, but since you know Green's function, it's just two lines. All right, so this is the picture. Now we think of it as a many-body system. So if I was a many-body system, really in any given sample, there's a bunch of eigenvalues. And so the things that Wigner and Dyson and many other people understood, that these eigenvalues have eigenvalue repulsion. They're almost equally spaced. They're not quite, but they're almost equally spaced. So they're really spread out, and the average spacing is 1 over n. So this is what it looks like. And so if you had some set of particles, you would just occupy all these levels. And your density of state at the Fermi level would be this rho 0, depending on your chemical potential. Now, this system is just a bunch of free fermion with some density of states at the Fermi level. So if I want to compute its specific heat or its entropy, I just use this exactly what you learned, the Sommerfeld expansion. You just apply it, and you get the Sommerfeld result of this entropy or the specific heat is n gamma t, where gamma is just pi squared over 3 times the density of state. This comes from the Fermi statistics. So rho 0 is the number you would get from the semicircular law, and this will give you the density of states of the system and the specific heat at low temperature. So it's a many-body free fermion system, and mu could be anything, so it's a compressible. It's just a random system. This is a random matrix theory. It's used for disordered metals all the time. As for quantum dots, this is a very good description of many, many experiments of quantum dots. Okay, but I'm going to think of this as a many-body system.
Subir,
yes.
Just to touch base. So go back one slide. The calculation of the density of states was purely spectral theory. You have some temperature there.
Yeah.
Is that just for students or also for me, honestly? Is the calculation changing that much with thermal occupations? Because temperature was not an ingredient.
Well, these are free fermions. So all I did is just I diagonalized the Hamiltonian, which is given to me. And then I just occupied state with the Fermi distribution function. That is the exact answer. That is the total answer. Now, when in the limit, when the temperature is smaller than the bandwidth, which is T, then this is the full answer. But you can write down the full answer in terms of Fermi function, which is valid for all temperatures. This is just the low temperature limit, which I use using this for Sommerfeld expansion. So, I don't know. I always look up the appendix of Ashcroft and Mermin. That's exactly, this is all this is. You have the full expression for, in the usual textbooks, you have energy as a function of momentum. So the only difference is that here is a function of alpha, just integrate over alpha. This is all you need is the density of states in the end, right? Even in the Sommerfeld expansion, all he needs is the density of states. Yeah. Okay, so this is a numerical calculation where you compute the density of many body states, okay, just for fun, for now. So we take n particles, or in fact, in the grand canonical ensemble, you put any number of particles. So how many states do I have? Well, I have n single particle states. So in the grand canonical ensemble, I have 2 to the n states, because every state could be either empty or full. So I have 2 to the n states. So now I want the density of those 2 to the n states, okay? So how do I build the 2 to the n states? I just do it this, n alpha is 0 to 1, so there's 2 to the n values of n alpha. And so if a state is occupied, I put n alpha equals 1. If it's empty, I put it 0. I add up all the energies, and I get the excited state from the ground state. Okay. So if I compute this energy, and I compute that density of states, nobody knows the actual answer for that, even for this problem. That's the result you get. So what you see here is that there's this long tail, and then there's some very dense set of states. Okay. So first, let's think about what happens when the energy, you're somewhere here. So this is a regime where the excitation energy is of order n. That means it's an intensive regime where you've got some finite energy per particle. Okay. So in that regime, you can use thermodynamics. So in that regime, Boltzmann told us that the density of states is just that's the definition of entropy. D of E is exponential of S of E. Now, I don't know what S of E is, but I know what S of T is. I just computed it. And then you just use some thermodynamics to go from canonical to microcanonical ensemble, and you deduce that S of E is square root of 2n gamma E. So E is of order n is of order n, so this is of order E to the n. So when your energy is extensive, the density of states is exponentially large in n. That's true for any system. It's true for my cup of coffee. The total number of states is exponential of the entropy, and the entropy is extensive. So that happens here when your energy is extensive. Gamma is the Sommerfeld coefficient, is exactly this. Same thing, which depends on where you put the chemical potential, but whatever.
Where the square root is coming from?
Okay, I have to show you this then.
Looks important, right?
I hope I can get it
linear
right.
in T entropy.
Okay, this is just a bit of thermodynamics. Okay, so we know that, let's see.
Maybe I should know or remember.
No. I also didn't know when I first looked at this. So S, we have said, is N gamma T. Okay, that's the entropy valued. Then what do we know also? That S is minus dF dt, right? So the free energy is, then you integrate this for the free energies, it's some ground state energy, E naught, minus 1/2 N gamma T squared, okay? So this is the free energy. Okay, and what is the energy? Well, the free energy is E minus Ts. So this tells me that the energy of the system is E naught plus 1/2 N gamma T squared. Okay, so this is one result here. Energy has to increase. It cannot go down. Free energy goes down, but okay. So now you combine this with this, and E naught I put equal to 0. You will get that. No, this is this very strange thing. You get E to the square root. Yes, what is that? Well, that's all it is. You all know those equations. All right, so that's what you see here. Okay, but then what about way down here when the energy is not extensive? What's happening when the energy, so look way down here, this is now, so here the density of states is exponentially large. But way down here, the density of states is not exponentially large, it's of order n. Now, how do I know that? What happens at very low energies? At very low energies, when energy is becoming non-extensive, what are my excited states? Well, the only thing I can do is take an electron, occupy one of these empty states, or occupy one of those, remove an electron from those states. So, it's a very simple thing. I just remove a particle or I add a particle. Since the spacing is 1 over n, it's going to take me energy 1 over n. Okay? So when the energy becomes non-extensive, the spacing between these levels is 1 over n. Okay? And so the density of states is quite small. So this is also a very robust property of not just this simple system, but any system with quasi-particles. The density of states at very low energies becomes of order n, not e to the n. All right, now let's go to the SYK model. It's essentially a random thing, except Now the electrons are going to only interact with each other with this interaction parameter u. And so here's the Hamiltonian. I end at what time? Oh, okay. But before I go there, any questions on the matrix model? Hopefully everyone understood that model. Yes?
So I started not worrying about the space organization, but at some point I need to see that I have some kind of...
Yeah, so right now we're just solving toy models.
Okay.
That is the purpose of my next lecture, is to now, I mean, so we're going to do 2 steps. First, we're going to put interactions. And, you know, it turns out that's the right order to do things. Interactions are actually easier to deal with in a fully random system.
Yeah.
And then you put in space.
Okay.
Then that's, you know, that's the summary of, I don't know, last 10 years of my life. If you do it that way, you can solve the problem. If you do it the other way, nobody could solve it.
Okay.
Okay, so now we're going to look at this model, which goes back to a closely related model we talked about a long time ago. Here it is. Okay. So now it's very much like the random matrix model, except the random term is just interactions. So there's now 4 labels. Now I'm calling alpha, beta, gamma, delta. And there's a u alpha, beta, gamma, delta, which is, you know, if you had a very complicated atom, you have exactly this Hamiltonian. These are called the Goodenough-Kanamori interaction terms and so on. Like you can look up a table of all these numbers for these alpha, beta, gamma, delta for some atoms. There's also some, now of course there will be some hopping in general, there'll be some dispersion, but that's the main thing. We're going to ignore hopping. There is no dispersion, there's only interaction. You know, why would we want to do that? Well, we had some reasons way back when we were thinking in terms of spin systems and spin-ons. It was a very natural thing to do for the spin-ons. I think also Kitaev had a different motivation coming from Majorana fermions, where under certain conditions, the interactions were not allowed, and so on. Okay. But of course, in the real system, like the cuprates, we have to put in dispersion. This is related to your question. We have to put it in. It's not, and that's what many, you know, I'll turn to that later. But for now, let's just try to solve this model. Yeah, so for whatever reason, we were lucky enough to first think about solving this model, and it turns out to be very, very instructive anyway. Okay, so now, first of all, so basically, again, this we take this u alpha, beta, gamma, delta to be independent random numbers with mean square value u. And that's really the only parameter, and there's, of course, the density. There's a conserved quantity here, which commutes with the Hamiltonian, and the density goes q because we're in 0 and 1. Now I'm ignoring spin here. Okay, so again, you can put this on a computer, but now it's much harder because you really have to diagonalize a 2 to the n by 2 to the n matrix. For free fermions, in the many-body sense, if you had a Hilbert space of size 2 to the n, you could only have to diagonalize an n by n matrix. Here, you have a Hilbert space of size 2 to the n, and you have to diagonalize a 2 to the n by 2 to the n matrix. So you can do, you know, these days with all kinds of symmetries, up to n35 or something like that. Whereas for the free fermions, it's easy to do 10,000, no problem. Okay, but it turns out, amazingly, the Dyson equations are very, very similar. You do diagrams. That's one way to do it. So you have a you treat everything as a perturbation, except the chemical potential, and you do exactly what I did. So I won't do it on the board, but actually it's exactly the same. Again, only one diagram survives. All other diagrams are down by 1 over n. Just do exactly the same thing, draw the pictures and match the indices and look at how many free indices you've got. There's only one diagram, and it's this one. So this is sometimes called the melon diagram by string theorists, because, I don't know, there are more other models which they now call SYKQ model, where there's Q lines here, and then it starts to look like a melon. But with 3 lines is not quite a melon, but anyway. This is it. This is the only diagram. This is another diagram in order U squared, but it's down by 1 over n. So sigma is now G squared times G cubed, basically, with the U squared here and all. So now you have to solve these 2 equations. So you have 2 equations for G and sigma, and you have to solve 2 unknowns, but they're both functions. But now for the free fermion problem, you could just go to frequency space and the equations decoupled. For each frequency, you had a different equation. You just had to solve a quadratic equation. Here, there's actually an infinite number of equations for each, because they have different equations for each frequency or each tau. And they're all coupled to each other, because if you now write this in frequency space, you see that this involves an integral over many, many frequencies. So you have an infinite, it's really a solution of an infinite number of variables. You have to solve it. Right, so we solved a little bit about it, and I'll show you that solution soon. Today, I think, with the benefit of all these very fancy conformal technology, turns out that this, unlike the beautiful thing about this is that, unlike the model here, or the Hubbard model honeycomb lattice, I had to go to a very special point to find a conformal structure with Planckian dissipation. Here, it doesn't matter. As long as your mu is in some range, at low energy, it's always Planckian and conformal. So it somehow seems to flow to the fixed point universally. And some of that we understood already a long time ago, and now is understood in great detail, what the low energy Planckian theory is. And it turns out to be the dual to a theory of black holes and with charge. And that's, so somehow to understand the full solution of these equations, you need to know something about Einstein gravity. If you had told me that in '93, I would have told you you're crazy. But okay, that's what happens. Okay, so let me try to give you a flavor of what the solution looks like, at least at low frequencies, which we can understand quite a bit. But even here, what you can do now today is not just the conformal solution, but all the corrections to conformal we can also get. But let's do the simple thing, which was already done by about 2000 by us, and also by work by Parkole and George that I did with them. So for this, I want to show you exactly how it all works. Let's see. Yeah, okay. Yeah, I think I have enough time to show you this. So here we do the path integral. We just write down the path integral for this thing. And I just average over U. So I just do the average in the path integral for each time. And when you do the average, this is what you will get. This is just the free fermion part. And this comes from the average over U. So when you average, by the e to the u times something, you get u squared, and then you'll get 4 fermions. So that's, so you get 8 fermions there, because when you do the average over this, you have 4 in each u, and that comes with 8. And you have to keep track all the times and the indices carefully, and you can write it in this compact form. Now, A and B are replica indices, but just ignore them. You don't really need them in the end. So now you do this trick. You just insert unity is equal to this. So what is this? This is just if I do the integral over sigma, so sigma is some field of both 2 times, tau 1 and tau 2. If I do the integral over sigma, this tells me delta function of g is equal to this. And then I do the integral over g, integral over delta function is 1, and therefore this is 1. Okay? So this is just a trivial identity of sigma is going along the imaginary axis. So that gives you delta function, and then the integral of the delta function gives you 1. So this is completely trivial. But now I'm going to, of course, insert this in here and use the fact that when I do the integral over sigma, g becomes equal to this. So everywhere in here, I can replace this by g. And of course, g is just the Green's function, which is exactly what's appearing here. So I can write the partition function as a path integral over this quantity g and this quantity sigma, and this action. And what happens here, I mean, I know this is a bit technical. Once you put the g here, the thing becomes quadratic in C. C only appears here and here. This is very similar to the Hubbard-Stratonovich transformation that we did earlier. You can do the path integral formally over C, and then you get this trace log. But anyway, it's not, you don't really need to understand all of this, but they just put it up there so you see it. So what are this g and sigma? Well, these are precisely, so there's a path integral over g and sigma, but the physical g and sigma are the expectation values of these fields. So this is a very general thing, actually, you can do for any field theory. You can write it as a path integral over the Green's function, sometimes called the Luttinger-Ward functional. Okay, if you just look at the saddle point equations, you get these equations. So you can breathe a sigh of relief, because I got the same equations by a much simpler method over here. Okay, now you can, all right. The reason for doing it this way is that certain of the symmetries are a little easier to see. All right. So now let me show you, let's try to solve these equations at very long times. So we go to 0 temperature and ask for the solution of these equations. This was something that was already in my first paper in '93. Okay. So you have G. Let me ignore the mu, put mu equals 0, and so on. So it's I omega minus sigma, and sigma of tau is minus u squared g cubed of tau. So when mu is 0, everything becomes an even function of tau, so I don't have to worry about the signs. Okay, so let's make a guess. Well, first of all, we can make a guess, what does mg look like as a function of frequency? In a Fermi liquid, it'd be just some constant. Okay, it's gapless, and but here, okay, could it have a gap? Like in a BCS superconductor, there'd be a gap. Could the solution have a gap? Well, you can see that, in fact, it cannot have a gap, because suppose G has a gap. So mg is 0 in this regime. This tells me m sigma is also 0 in this regime. Okay, there's a gap delta. All right, now if G has a gap, that means at long times G will, in imaginary time, will decay as e to the minus delta tau. So G cubed will decay as e to the minus 3 delta tau. So this means sigma will decay as G cubed e to the minus 3 delta tau. But from this equation, I deduce that sigma decays as e to the minus delta tau. So that's because the gap in G must be the gap in sigma. This is a contradiction. So delta has to be 0. The only possibility is there's no gap. Okay, if there's no gap, what can it be? Well, if there's no gap, so you make a guess. I shouldn't have erased those equations. You make a guess, let's say, what should we guess? Yeah, so G of tau goes as 1 over tau to the alpha. And that tells me that G of omega, which is the Fourier transform of this, up to some constants, d tau will be omega minus 1. Because it's d tau over tau to the alpha. This gives you an alpha of omega. Yeah, okay. Just for dimensional counting. Some constants and then, okay. So then sigma of tau must go as tau to the 3 alpha. And then what is sigma of omega? Well, that tells me that sigma of omega must go as omega to the 3 alpha minus 1. Okay, now how is this possibly consistent with this? So I have these low frequency dependencies. Well, this can only work if, first of all, this is larger. So what we want, this power to be smaller than that power. So we want 3 alpha minus 1 to be less than 1. Otherwise, I can't throw this out. So you can throw this out now. And now for this to work, this must be the negative of that. So 3 alpha minus 1 must equal 1 minus alpha. And if I did this right, that tells me alpha is 1/2. So that's the conclusion, that g of tau goes as 1 over square root of tau and also 1 over square root of omega.
Subir, can you repeat just acoustically the last step?
Yes, that was very quick.
Now, for the alpha minus 1 smaller than 1, maybe I got that, maybe other people didn't.
Yeah,
but the
argument is that there are two terms here. We are only interested in small frequencies or long times. And if this is larger than that, this is much smaller than that, then you can ignore it. Then if you can ignore it, the power here must be the negative of the power here, which is this equation. Everybody got that? Okay. So that's 1 over square root of tau. Okay.
Just to also give people time to catch up.
Yeah.
You said something before that for mu equal to 0, there are issues with the Planckian relaxation, and now you said mu equal to 0. Did I get it wrong? Like in the stream of thoughts at the beginning when you introduced the model, you were making remarks that if mu is equal to 0, there is something weird happening. Did I get it right? No.
No. So there's something weird happening for the honeycomb lattice model. There you have to put mu equals 0. Only then you get the Planckian physics at the Dirac
That's
point.
clear.
Here, no, there's nothing special about mu equals 0. I assume mu equals 0 for simplicity, because then the function, everything becomes an even function of tau and frequency. If mu is not 0, it's more complicated. But can be done, can be done.
But you get the same? You get
the same power, but you get also some different coefficients on the two sides.
Sure.
There's some particle hole asymmetry, which is actually quite important, but I don't want to. No. All right, so that's, you don't need to know any fancy stuff, because we certainly didn't in 93. You wrote down these equations, and we said, okay, g of tau must go as this. And we did some numerics, and it seemed to be okay, so computers were much more primitive in those days. Okay, so here's, basically, forget about mu. We just, this mu didn't matter, okay? And we got this result. All right, so now let me just take these equations again and just rewrite them. So this equation, I'm now going to think of sigma and g as functions of 2 times, which is what comes in the path integral. They're really functions of 2 times in general. They're functions of 2 times because you get 2 times here when you average over disorder. So they're functions of 2 times. The actual physical g is the average value, which is only a function of time differences. Okay, but let's just, for the fun of it, rewrite this equation, which is the same equation, as this way. So this is sigma of tau 1, tau 2 is tau 1, tau 2, tau 2, tau 1. So that's the minus there and the square over here. So this is the same equation as that. And this equation I'm also going to write in time. But I'm going to drop these 2 terms because this term didn't matter. So I'm only interested in the low frequency behavior. This term didn't matter. That's g times sigma is equal to 1. If I write it in time space, it's the integral over the common time. Sigma times g integral over tau 2 is a minus the delta function. Okay. So at low frequency, what's giving me this solution is just these equations. I didn't need the omega. All right. So we take these equations, which I wrote them here, and you find a magical property. It's kind of amazing. This equation is invariant under time reparameterization. So That means you have some clock, tau, which is running along a circle in imaginary time. And you have another clock, which is running fast and slow, which is the sigma clock. There's a sigma clock and the tau clock, and they run at different rates. And so you could choose to, you can work in the sigma clock or you can work in the tau clock. It doesn't matter. The equations that you will get are the same. And this is the G and sigma and the tau clock are related to the G and sigma, which are the G tilde and the sigma tilde in the sigma clock by this transformation. And I urge you to just insert this into these equations, and you will find that the sigma tilde and G tilde equation in the sigma 1, sigma 2 variables are exactly the same. This is exactly what happens in Einstein's gravity. You have the Einstein-Hilbert action in some space-time metric. You choose some space-time coordinates. And then you do a coordinate transformation to new space-time coordinates with a new metric. But the action is exactly the same in the new variables. It doesn't depend on the choice of your space-time coordinate system. So here you have an emergent, low-energy, time reparameterization symmetry, whereas Einstein's equation have an emergent space-time reparameterization.
The object that is invariant in Einstein gravity is the curvature. So sorry, the network tensor G mu, right?
The action would have the same form.
The action.
Right. So here also you can also look at the equation of motion. The equation of motion is not invariant but have the same form. So in one coordinate system, the equation of motion is G mu nu equals T mu nu. Right? Mm-hmm. That's the equation of motion. You go to a different coordinate system. Of course, these are not invariant quantities. They have different values, but the equations are the same. In the new coordinate system, it'll be the same equations. So that's exactly what happens here. If you substitute this into those equations, you'll get the equation with the tilde variables, and sigma 1 is exactly the same. Maybe I should write them out here.
So the statement that is in SYK, okay, the first one is the Dyson equation, right? So
yeah.
There's nothing to discuss. And the sigma, you are saying if you do the reparameterization, will stay a G cube? So
yeah,
I'm trying
it'll be
to
the same equation. It'll look exactly, just replace all sigma and G with tildes, all tau with sigmas. You get those equations, same equation. So they're not invariant, they're covariant. Yeah.
Okay.
The action is invariant, the scalar
covariant.
curvature is invariant, but these are covariant, yeah. And the covariant because, G is not equal to G tilde. It has all these conformal scaling factors out front. Well, this equation, okay, this is a subtle point. I'm presenting it in a way that the simplest way to understand. It took a ridiculously long time for this to be clear, what I've just said in 5 minutes. So don't worry if you're confused. This form was already there in 93. Then in 98, there was a paper by Parkole and George who noticed something. I don't know if they knew this, but what they noticed is the following, that if you did a conformal transformation for this very special conformal, which is what you mentioned, you map the line to a circle and the plane to a sphere. You do that conformal transformation. That particular transformation, the equations were invariant under those. But in this full form with both times, I think Kitaev was the first to say that. In this full form like this, well, actually, yeah, Kitaev had it without the little g. I added the little g, and so on. But he really was the first to say that when you take the two-time equations, then the structure becomes much clearer. Yeah, there has to be those exponents. Yeah, I mean, that exponent, those exponents are very easy. This 1/4 is just related to this half of the 1/2. That's a very general thing for conformal symmetry. In fact, I probably knew that too. The scaling dimension of the field is 1/2 of the decay. That's all. This is just the scaling dimension. This is trivial. Getting these exponents is trivial. Making these factors space-time dependent is then space-dependent. That's the conformal structure here. Okay, well, I mean, all of this is to say, you can use this symmetry of the low energy equation to go from this behavior as square root of omega to get full answer as a function of omega over t. So the thing we were struggling for the honeycomb lattice model, this is it. This is the full answer, at least for the Green's function. It has Planckian dissipation. You get, for the Green's function, and particle hole symmetry is this line. It falls off as 1 over square root of omega, and as function of omega over t. It's completely smooth here, and there's a factor of 1 over square root of temperature out front. And so the spectral function, if you did some kind of tunneling experiments, you would see a width of order temperature. And this is something you get, what was just a dream for the honeycomb lattice model, you can just get it here within a few lines. I mean, all the steps are here. You just have to do some Fourier transforms and so on. Okay, so what we have learned, and that's really mostly what I wanted to say, is that the SYK model is a strongly interacting model of electrons. In fact, it has no dispersion at all. It's like a flat band model, if you wish. It's a flat band with random interactions. That's SYK. And there are also many papers in the literature to somehow take all these new flat bands that people are finding and put in some randomness, and maybe there'll be SYK physics. Yeah, we'll see. I mean, there are some indication in graphene, in fact, of that. I was a paper with Philip Kim on that. Anyway, so it's a flat band with lots of strong interactions. And what we learned is that there are no quasi-particles. Everything is interacting so strongly that there's no well-defined quasi-particles. And furthermore, they have this Planckian form. Okay, yeah.
Wait.
Well, so I think it is quite important for the problem that we solve. People have looked at other models where they do sparse connection, where they randomly remove some fraction p of the bonds and things like that. And that still works.
So this is why you're saying it's like a flat band, even though they are not all-to-all connected?
Yeah, but if you add in the hopping, the Tij, then you immediately lose the structure. Not immediately, but at low energy, you go back to the first part of my talk. You go back to the thing where your density of states was constant with the rho 0 and all the Sommerfeld results. The Sommerfeld doesn't apply here. Actually, that leads into the next point. Now I'm going to talk about the entropy of this thing, which turns out to be quite different. Okay, so then from this, you got the Green's function, but we want to now compute the density of states. Of course, here, the density of many body states, the entropy, because, well, entropy is something you can measure. You measure the specific heat. You can ask what will be the specific heat of this thing. Yeah.
Just maybe, no, it's a technical, not related to physics. So because 10 minutes are missing to one, can we have maybe extra questions and you continue tomorrow, or you have a few slides to finish in SYK? I just don't want to cut you a few slides from the end, but if you have...
I just want to show...
Okay, if this exactly. That was my question, yes.
Yeah, okay. Let me just show this slide.
Yes,
because
yes.
it connects to the first part of my talk.
Yes.
And then we'll stop. Yeah. All right, so this is the same. This is a numerical calculation. In this case, only of 16 electrons of all the states of SYK. Okay, so I'm going to connect. Well, maybe it's over here. Yeah. So I showed you this for the random matrix model. So they've had an exponentially large density of states, which was e to the square root of e, and then it went to 0, this long tail. Now we go to SYK, there's no tail. There's no tail at all, it just goes very rapidly, it seems to be exponentially large everywhere. In fact, that is correct, because now the entropy, strangely enough, is not equal to this. There's this constant offset. Okay, now before you say this is violating some law of thermodynamics, it's not. uh, it's not a ground state entropy, it's a zero temperature entropy. Those are very different things. So let me try to explain that carefully. So we're taking n to infinity first. We're taking an infinite system, and then we're sending temperature to 0. Then you find that there is this S naught, which was computed by us, by GPS somewhere, by Georges Parcolet and myself. What does this mean? It means that the density of states, when you go to very low energies, is exponentially large. And what that means is that the level spacing, remember the level spacing here, was that forward? Oh, no. Level spacing here became very sparse, became 1 over n. Here the level spacing is e to the n. It's huge. And that's why there's no tail. The levels are still very dense down to the ground state. There's no degeneracies. They just randomly lots of states at very, very low energies. And this is, in fact, proof that there are no quasi-particles, because if you had any kind of particle description, the spacing will be 1 over n. That's how many particles you can have. There's no single particle description. They're very, very chaotic states in this exponentially large Hilbert space. And one state and the next states are totally different from each other. So what happens here, here you have a ground state. Okay, maybe it's complicated. What is the first excited state? The first excited state, you take the ground state and you just add a particle somewhere. And it'll change a little bit there, and that's about it. It's pretty close. These states are all very similar to each other. That's the essence of a quasi-particle theory. But now here, one state and the next are completely different. They're just chaotic states. There is no there's no simple difference between the states. That's the essence of absence of quasi-particles. In this case, there's no quasi-particles. It's down to 0 temperature. And that leads to the 0 temperature entropy. Then using gravity, you can also get the correction, the Sinch function. This part is just the same argument as before. Anyway, so there's a whole bunch of technology that I don't need anyway, because this is all special to the SYK model. But it kind of is a picture that makes the physics of absence of quasi-particles very clear. Okay, thanks. So now it's time for questions.
So mine, I think, is much more curiosity, actually. The invariance in the chosen of the taus there in the G functions is somehow related to the fact that evolution in time doesn't have like a preferential direction. Like I could choose change t for minus t, and still happens. Like.
Well, I mean, here it's a kind of an emergent symmetry. There is a preferential direction, which is given by the term that's, kind of was irrelevant. So, there is this z there, this omega. Mm-hmm. It is there, and that is not invariant under time reparamerization. So, if you just go beyond the leading term, you immediately have a clock. There's a preferred clock. It's there. So you do have to softly break this time reparamerization. Mm-hmm. But it's still a very useful thing. It's like conformal invariance also. Like when we talked about even the graphene, yes, there's a low energy theory that's conformally invariant, but actual graphene is not. I mean, there's always something that breaks it. Mm-hmm. Here, there is something that breaks it. So it's the usual strategy. You have some emergent symmetry at low energies. It's good to understand what that emergent symmetry is. And then you think about how it's broken. And then you ask, is the breaking important or not? Mm-hmm. Now here it turns out, because it's such a big symmetry, huge symmetry, it's not just some rotation symmetry, it's an infinite dimensional symmetry. Mm-hmm. How you break it actually is important for various things. And in fact, to get this, to to get this, this square root E here, you do have to understand how it's broken. Oh. Is the leading theory, this term comes from the fully time representation theory, but to get this and to get the cinch function, that's all about exactly how is the time reparameterization. How to
so I can change the clocks, but I cannot change the direction of I'm choosing to go in time.
Oh, that, of course. No. That's absolutely. The symmetry requires that these functions f have to be monotonic. Oh. They're monotonic and they don't have any loops. You know, you can't go backward in time. Okay. They're always going forward. They're monotonic, but they can run in different rates.
Okay.
Okay. That's required. There's no violation of causality, and there's no closed time loops or anything like that.
Thank you.
Yeah, I have a question related with this exponentially closing of the eigenenergy.
Yeah.
So is that somehow related with like spin liquids where you get like, but in that case it's like a massive degeneracy, I understand. So is there a connection there?
So spin liquids don't have any degeneracy. I mean, well, okay, if you have this dimer picture of, quantum dimer model, then yes, of course, all the dimer configurations are leading order degenerate, but then there's resonance and that lifts the degeneracy. So now here, the fact that there's a ground state zero temperature entropy is very special to zero-dimensional system. Once you go to finite dimension, this will disappear. Nice. So this is, it's really very special here. In fact, we discovered, that's one of the reasons we stopped working on the SYK, what's now called the SYK model. So in this paper with George and Parcolet, when we got this S0, 2001, we said, that's ridiculous. How could any real system have a zero temperature entropy? This may, but, well, later on it turns out there are black holes that do have a zero temperature entropy. And so this was perfect for that, but that came much later. It took me about 2010, 9 years later that I understood that. But for about 9 years when we should have been working on this, we didn't work on this because of this. So it's very special to 0 + 1 dimensions. Yeah.
Thank you.
Yep.
Well, the absence of quasi-particles is not, but so this is a system where you can prove, where you can, absence of quasi-particles is such a strong signal that you can see it. You can prove it. In other systems, it's a little more complicated because, for example, here in this system, I said there's no quasi-particle because I don't see a pole. Okay. That was cheating, actually, because all I said was I don't see a pole in the electron Green's function. But maybe there's some complicated monopole vortex operator which has a pole. Can you prove? I don't know. Maybe it is. So I haven't really proved there are no quasi-particles. I've just told you that the electron particle doesn't exist. It could be some Laughlin particle or a Jane particle, something very complicated that has a pole. So I hadn't proven that. It's highly unlikely for that model. You have numerical evidence and so on. But here, because of this S0, I've proven there's no such thing.
Yeah, related question, actually. So in spin systems, the level spacing can tell you something about the integrability of the system.
Yeah.
Does this
Yeah, it tells you it's completely non-integrable.
Okay,
that's another way of saying what's nice about the SYK. It's shocking from our perspective because it's a sort of a solvable model which is completely non-integrable. It's as chaotic as it can get.
But it doesn't tell you anything about the solvability, right?
It tells you, I mean, it'd be extremely, there's no way an integrable system can have this property.
Actually,
except you fine-tune something, not generically.
Actually, I have a pressing question. I had exactly the same point of this guy and connected to that. So there is maybe here a point to clarify for everyone. So integrability implies solvability, for sure.
Yeah, okay. Yeah.
You want already to comment on that?
No, go ahead.
Okay. So, but it is not prohibited to have solvable models that are not integrable. So is this the first case that we have? Solvable but not integrable? Because otherwise there is a contradiction, right?
What do you mean by solvable?
So you have an analytic exact solution of this many-body problem, right?
In a certain limit of some average Green's function. What I certainly don't have is the energy eigenvalue of all those energies. In integrable system,
that's correct. We don't know the states.
You have to solve of order n equations. You solve of order n equations, or you diagonalize an n by n matrix, and you can get all of those eigenvalues. In this system, it seems like the only way you can get all those eigenvalues is to diagonalize an e to the n by e to the n matrix. There's no shortcut. And that's kind of what I mean. It's not integrable. And these are just chaotic states.
That's the confusion.
Which extend over all of Hilbert space in some way. I mean, there are some interesting papers by people in quantum information theory who are trying to quantify this more precisely. What is the complexity of this state? And these fermionic SYK states are about the most complex states known. I mean, maybe it's integrable. I mean, it would be shocking if it was integrable. I don't think so. Yeah.
Somebody would have to come up with equation to determine the states, as they do in Bethe ansatz, right?
Yeah, it seems hard to believe. Yeah, this is. Yeah, it's a system that behaves. It thermalizes in the record time. That's what it thermalizes in a Planckian time. It's the fastest possible. It's the worst possible quantum computer because it thermalizes as quickly as anything could possibly thermalize.
I had again a question. So I didn't quite understand the point that we can't have quasi-particles because they're okay. So when the states are chaotic, we can't have quasi-particles. But how do I see that they are chaotic?
Okay, just to get this many states, so to get exponentially large number of states at such low, even an energy about a 1 over n, I have an exponentially large number of eigenstates. Mm-hmm. I don't see how I can build that from a Hamiltonian without taking, and make them all orthogonal in this very tiny energy window by taking them, having them extend all over Hilbert space. Okay, so that it's just a reasonable argument. I'm not a mathematical physicist. I don't know how to prove or even specify these statements more accurately, but that's what I meant.
Okay, thank you.
I mean, mathematicians are now getting interested in proving rigorous things about SYK, but I've talked to a few pure mathematicians, but it's quite difficult, apparently. Or people in probability theory, Now they're proving things about the classical Sherrington-Kirkpatrick model. They're finally proving all kinds of things about it. This would be one step more difficult. Maybe more than one step more difficult.
Anything else? Thank you, Subir.